Okay, let's go ahead and get started. Our next speaker is Jim Hartford. He's going to be covering creating coherent, scalable, interoperable telemetry solution. Go ahead, Jim.
Good morning, all. 2025 was a year of major challenge for the OCP workstream you might have known as cloud service model. The group got me as a new lead. We got a new charter and a new vigor to pursue scalable telemetry. Now, we had done some previous work pursuing telemetry, and if you looked at our wiki page, you could find a white paper written a few years ago. But we really wanted to produce architectures and work with standards protocol groups to foster what I like to call coherent, scalable, and interoperable telemetry solutions, which is the topic of my presentation to you today. You can see our new charter on the slide. A recurring theme in our work is to ensure that hardware elements of a large data center can be managed well, and you will hear some of our ideas on that subject today. Remember that old joke about the best thing about standards is that there are so many to choose from? Today we see interest across the industry in many protocols that might be used to communicate telemetry information, including Redfish, Yang, Prometheus, and OpenTelemetry. Not only the protocols, but the data schemas and even the names for individual metrics can be different. Perhaps there are multiple protocols being employed within the data center at the same time. How can we bring order to the chaos such that equipment vendors can build components that can be integrated into large data centers, having different philosophies on how to best meet the needs of their stakeholders? Our answer is a four-step process, with the first step being to create a protocol-agnostic architecture for streaming telemetry. That is where we are right now. We are defining a set of top-level abstract semantics that will enable the industry to converge on general concepts of how to stream telemetry data. Then we will work with various standards bodies and open source communities to explore how our architecture can be mapped onto the protocols of interest. For the sake of time, I'm going to skip this next slide, but it contains some of the current trends we see in telemetry that have influenced our thinking. So let's climb into the fundamental building blocks of our architecture for doing telemetry at large scale. We have defined 5 types of nodes which cooperate to deliver telemetry information from original data sources across the data center network to the ultimate consumers of that information. A leaf node contains sensors which observe various aspects of interest and then emits those observations across the data center network. We're talking about interesting aspects such as temperature, power consumption, number of bytes transmitted, number of error packets received, CPU idleness, all kinds of metrics needed to properly manage data center equipment. Most of my talk today is focused on leaf nodes. An aggregation node is an intermediate node that aggregates multiple telemetry streams received into a smaller number of output telemetry streams. A filtering node is an intermediate node that removes certain information from telemetry streams to prevent sensitive information from propagating. A reporting node is an endpoint that stores and reports telemetry information of interest to authorized personnel and systems. A control node coordinates the flow of telemetry information from leaf nodes towards reporting nodes. As I said before, these nodes cooperate to convey telemetry information across the data center network. In these next 2 slides, a circle labeled L is a leaf node, A is an aggregation node, F is a filtering node, R is a reporting node, and C is a control node. The green arrows illustrate the flow of telemetry data between the nodes as data journeys through the network from leaf nodes towards reporting nodes in this very simple example topology. First off, notice on the right side that we have 2 different reporting nodes, one for network operators and the other for network partners. These partners could be data center customers, equipment suppliers, or other organizations with which the data center has some business relationship. The operators, at the top right, have full access to the telemetry data, but the network partners, at the bottom right, likely have access restrictions that prevent them from viewing sensitive information. I will say more about this later, but you can see that the network partners view telemetry data after it is passed through a filtering node, where such sensitive information is removed. In the example here, an aggregation node is combining some information from 3 different leaf nodes, resulting in a stream of information to a reporting node. The aggregation node is likely performing reduction operations on the data, such as computing the average, minimum, and maximum of some metric across different leaf nodes. In contrast, there is some telemetry data that flows directly from a leaf node to a reporting node, represented by the top green arrow. Regarding the scaling of topology, we place no restrictions on the arrangement of aggregation nodes and filtering nodes within the end-to-end path. Both types of nodes are optional, and the order in which one or more of them might be encountered along the path is determined by data center architects. Just to be clear, there could be an arbitrarily complex hierarchy of aggregation and filtering nodes used to manage a large data center. Notice that telemetry data does not flow through the control node. Instead, its function comes to center stage on the next slide. A control node is responsible to set up a stream of telemetry data between a sender and a receiver of that data. This includes discovery of other types of nodes, negotiation of stream parameters, starting stream data, stopping stream data, and eventual teardown of a stream. What is a stream? A stream is a dynamically specified set of meter observations that are periodically reported together. Each green arrow on the previous slide represents a unique stream. On this diagram, the gold arrows represent communication between a control node and the other types of nodes in order to dynamically set up streams. In the narrow context of telemetry data, you could think of a stream as what network folks like to call the data plane, and the setup and teardown of those streams as the control plane. Now we can look at how these two ideas, data plane and control plane, come together to transport telemetry data from a sending node to a receiving node. I know this is an eye chart. When we first looked at a push style of communication, where the sending node periodically determines that it is time to emit sensor data towards the receiving node, before any metrics are transmitted, the control node negotiates stream parameters with both the receiver and the sender. Then the control node sends a start signal to both the receiver and the sender. After this, the sender can begin sending packets containing various types of metrics to the receiver. The selected metrics, their order, the frequency of packets were specified in the stream setup procedures. In addition, at any time, the sender could convey notification of carefully defined events, which I will discuss later. When the control node determines that the previously set up stream is no longer necessary, the control node sends a stop signal to both the sender and receiver, followed by a teardown signal to both the sender and receiver. We think that push networks are more efficient and scalable than pull frameworks. However, we recognize that some data center operators will continue to use pull style for legacy reasons. With the pull style of communication, the receiving node is the one that periodically determines it is time to request the sender to emit recent sensor data towards the receiving node. The setup and the starting of streams in a pull framework is almost identical to its push style counterpart. After the stream is started, the receiver can begin soliciting metrics from the sender. Just like push style, the selected metrics, their order, and the frequency of packets were specified in the stream setup procedures. In addition, at any time, the sender could convey a notification of carefully defined events, just like the push style. In this diagram, the dashed line for the send metrics message is the sender's response to a prior request message solicitation message from the receiver. The stopping and the teardown of streams in a pull framework is identical to its push style counterpart. It's important to understand about these two message sequence diagrams is that the sender is not necessarily a leaf node. Aggregation and filtering nodes also send telemetry data. Likewise, the receiver is not necessarily a reporting node. Aggregation and filtering nodes also act as a receiver of telemetry data. Instead, think of the diagrams you see as representing a single hop within a multi-hop end-to-end information flow. In our architecture, a stream spans a single hop. Next, let's look at advanced functions of leaf nodes. While most of this functionality is optional in our architecture, we believe that they are crucial for enabling scalability to large data centers. The first such advanced function is for a leaf node to perform local aggregation. Imagine that the sampling frequency of some sensor is faster than the stream's reporting period. In other words, there could have been multiple sensor samples between successive packets containing streams metric data. In this slide, the green X's represent sensor samples, and the blue dashed vertical lines represent the reporting of a single value. Perhaps the most common design in these circumstances would be for the leaf node to report the most current sensor observation. But depending on the implementation, a leaf node may be capable of reporting alternate sensor values, such as minimum, maximum, or perhaps average of the multiple samples observed since the previous metric report. I need to digress for a minute to mention the concept of levels or scales of measurement. The values that a sensor reports may be classified into 4 categories: nominal, ordinal, interval, and ratio, based on the math we can perform on them. We can leverage more or less math depending on which category the sensor's reported values lie in. And leveraging more math can lead to more efficient aggregation and more valuable insights for management of data center hardware. The slide contains more details than I have time to adequately cover today. Let's advance. The second advanced function of leaf nodes that I want to cover is derived meters. Instead of a leaf node reporting the raw value of some observed phenomenon, the leaf might report alternate representations that are more useful for subsequent aggregation and statistical analysis. As an example, NIC vendors typically implement hardware counters to measure various quantities, such as the number of bytes transmitted on an Ethernet port, or the number of error packets received on an Ethernet port. The associated metrics reported are typically the raw contents of the hardware counters. But consider trying to fashion an aggregate measurement of those counters across multiple sensors. The aggregation node would have to maintain a shadow measurement of the differences between successive reporting periods for each leaf node and each metric. And what kind of manipulations are required for the data center's operations team to translate raw counter values into actionable trouble tickets? Instead of reporting a raw hardware counter, in this case, it would be far more valuable for the leaf node to report a rate. For example, the number of error packets received per second, or a utilization. For example, the percentage of Ethernet line rate filled with transmitted bytes. We've already talked about reporting minimum, maximum, or average values based on temporal aggregation at the leaf node, but we can improve on this. What if the leaf node maintained a running box minimum, maximum, or average across multiple reporting periods? The effect is a low-pass filter that could help data center operators weed out the noise while analyzing trends. But we can go even farther. Additional distillations of raw metrics could include calculating trend line gradients, standard deviation, and configurable percentiles at the leaf node. Now, your response to the slide might be, well, all that fancy math will be done in a big centralized server somewhere where there's lots of processing power. But thinking like that does not easily scale up to large data centers with hundreds of thousands of leaf nodes. Instead, we need to push as much processing as possible out to the leaf nodes, which collectively contain much more CPU power. Equipment vendors often design telemetry support into their products with a minimalistic mindset, asking the question, what can I easily measure? As an industry, we need to shift the question to be, what can I easily analyze? In some cases, data center managers would prefer to avoid receiving periodic metrics observations. Instead, a manager might wish to be notified only if there's some anomaly occurring. The third advanced function of leaf nodes that I want to cover is threshold crossing alerts, sometimes abbreviated TCA. In this scheme, the data center manager would configure thresholds to determine when some aspect of interest had crossed from normal into increasingly dire regions. This could be configured in both the positive and negative directions from whatever normal is. As you might guess the name, when the observed measurement crosses a threshold between two regions, an alert message is sent from the leaf node. Note that this alert is done within the context of the stream. The alerts showed up as event messages in the previous sequence diagrams I showed for the push and the pull frameworks. Now let's turn to the actual format of the telemetry data on the wire. We must be cautious here because we're trying to describe semantics, not the detailed arrangement of bits flowing across a wire. We will attempt to specify certain aspects of the data format on the wire, yet still leave freedom to the actual protocols to define the complete format. We have several goals in mind for packets carrying telemetry data, and you can see that on the slide. Note in particular that the ordering of metrics, which you've heard a couple of times already, is specified by the control node during establishment. You might be thinking that the first few list items here sound like typical design goals, but then we swerve into Never Never Land. Over the next 4 slides, I will attempt to show how achieving these goals can lead to dramatic performance and scalability breakthroughs. On the right slide, yeah. As the slide illustrates, a packet containing telemetry data has a general heading appearing first and then is divided into a number of sections. The sections do not have to be the same length, but each section is composed of metric observations that are the same type, that is, integer or floating point, and they have the same width. What we have here is a collection of metric observations in which all possible redundant information has been removed. The identification of each metric, for example, temperature or power or received packet rate, is known from its position within the packet. During the setup of the stream, the control node negotiated an arrangement between the sender and receiver such that the temperature would appear first, the power would appear second, the received packet rate would appear third, and so on, just as an example. Instead of a TLV format, we only have the V's, the values. I told you that each section is composed of metric observations that are the same type and the same width. Since only metric values appear in the section can be imagined as an array of metric values. Within the example here, we have a section of 64-bit unsigned integers, a section of 32-bit signed integers, and a section of 16-bit floating point values. The sections begin and end on 64-bit boundaries, with padding as necessary at the end. This next slide shows the original motivating factor for the format that I've been describing. When multiple leaf nodes are all sending the same metrics in the same position within the packet, then aggregation among multiple leaf nodes becomes much easier. As an example, imagine that we have 8 leaf nodes sending metrics in the order you see on the left side of the slide. At the aggregation node, the arrays can be placed within memory such that vector instructions or even GPUs could be leveraged to efficiently aggregate the data. We believe that this approach is a natural result of the scaling that AI forces upon data center management. But there is another motivating factor to this highly compacted format, illustrated on this slide. When the reporting node is storing the data, we imagine that the arrays could be appended to tables in a large relational database. Then SQL queries, you see them as Q1, Q2, Q3, Q4, they summarize each metric. Each metric summarization becomes a column operation across multiple tables, each having the same layout. Again, we believe that this approach is a natural result of the scaling that AI forces upon data center management. I want to spend a minute talking to you about filtering nodes. There are several reasons why a data center might share a subset of telemetry data with external parties, such as its service providers, customers, or equipment vendors. Even so, much of the data must not be shared with the external parties. For example, many data centers consider the number of servers and the distribution of those servers among locations as sensitive information. Another example is that the data center may wish not to disclose functional and performance anomalies of its network. Finally, if a data center uses multiple equipment vendors for some functionality, metrics that expose those aspects of a vendor's design or reveal flaws would be sensitive to each vendor. In other words, it would be inappropriate to share vendor A's dirty laundry with vendor B. And so the telemetry infrastructure must include ways to strip sensitive information out of streams that would be eventually available to external parties. Filtering nodes perform this function. There's an old rule of thumb that an audience will only remember about 10% of what they hear in a presentation. I would like for this slide to be part of the 10% that you are going to remember. This slide has the big ideas of SCIM's current work on scalable telemetry. Dynamic setup of stream parameters. State information maintained at both the sender and receiver. Meter value representations that are useful for statistical analysis. Push complexity toward the leaf nodes. Packing formats that can leverage vector instructions and GPUs. Prevention of inappropriate disclosure of sensitive telemetry information. I made an implicit promise in the title of this presentation that the architecture path we are working on leads to telemetry solutions that are coherent, scalable, and interoperable. Do those claims hold true? Did I keep my promise? Regarding coherency, the protocol-agnostic architecture we envision shall specify semantics that form a complete system supporting robust telemetry solutions for emerging data demands. Regarding scalability, our architecture contains mechanisms that allow scaling to very large networks, including leveraging statistical tools to ease the crunch of metrics analysis. Regarding interoperability, when telemetry protocols and schemas are employed that conform to our architecture, interoperability should be expected, even in the face of multi-protocol telemetry support infrastructure. And finally, I want to invite the community to provide valuable feedback and participate with OCP Skim in our quest to build a better data center. In particular, we need more involvement from hyperscalers to ensure that our work is aligned with your needs to manage your data centers. This slide lists specific ways in which you and your colleagues can help us. The URLs at the bottom of the slide will take you to the web pages for our work stream. Thank you for your interest and attention, and I would be shocked if we have time for questions.
Yeah, we don't, but let's thank Jim, and then if you have a question, you can ask him offline.